Hi, we calculate the Earth's radius at the harbor. Here is the problem. A cruise ship leaves the coast at a constant speed of 26 kilometers per hour in a sunny day. The height of the ship is 36 meters above the water level. A 1.69-meter tall observer is watching the cruise ship from the coast. The cruise ship disappears into the horizon 1 hour after leaving the coast. Use this information to estimate the radius of the Earth. If you want to solve the problem yourself, we can stop the video here. Okay, here is how we solve this problem. We have the observer and the ship. We first need to see how we see the ship. Here, three lines represent the light arrays that reach the observer's eyes from different parts of the ship. We have one reaching from the top of the ship, one from the middle, and one from the bottom. When the ship moves further away, the lowest light array that connects some part of the bottom of the ship to the observer while not cutting through the earth, in other words, being tangent to the earth surface, does not come from the very bottom of the ship. So any part of the ship below that lowest line is invisible to the observer. When the ship moves further away, the lowest line that is still tangent to the earth only covers higher parts of the ship. Therefore, smaller and smaller parts of the ship are visible to the observer. And finally, the ship reaches a distance where the line that connects the observer to the ship and is tangent to the earth level only connects the tip of the ship. At this stage, all of the ship is invisible and the ship has disappeared. Now we replace the ship and the observer with two lines with the heights of h1 and h2. Move everything to the left and zoom out so that the center of the earth is visible. Now we name the tip of the observer and the tip of the ship A and B and connect the center of the earth to the tangent point of the line AB to the earth and call that point N. Now we draw the other two radii with the lengths of R that connect the earth center to the bottom of the observer and bottom of the ship. We call the distances or the lengths of lines AN and NB, D1 and D2, and the associated arcs S1 and S2. We move everything to the left to a space for some algebra. Now this is a geometry problem. Now we can use Pythagorean theorem for triangles OAN and OBN. For OAN we have r plus h1 squared minus r squared is equal to d1 squared, and for triangle OBN we have r plus h2 squared minus r squared is equal to d2 squared. We expand the equations, r squared in both equations cancel out each other and we end up with a simpler equation. Now in these equations we have lengths d1 and d2. However, we know that the distance of the ship is in fact the summation of S1 and S2. Therefore, we need to use an estimation. Now, this estimation is what makes our solution a physical solution rather than a mathematical solution. So this is a physical estimation. We know that the distance that the ship takes is 26 kilometers because the speed of the ship is 26 kilometers per hour and it takes 1 hour for the ship to disappear. So the total distance is equal to 26 times 1, which is equal to 26 kilometers. This 26 kilometer distance, which is the summation of S1 and S2, is thousands of times more than the height of the observer and the height of the ship. Therefore, we can assume that S1 is much greater than H1, which makes the triangle ANA prime a very skinny triangle. Therefore, we can assume that S1 and D1 are almost equal or approximately equal. Similarly, we can assume that S2 and D2 are approximately equal. Therefore, in the top equations, we replace D1 with S1 and D2 with S2. So we have equation 1 now and equation 2. 2RH1 plus H1 squared is equal to S1 squared. And equation 2 is 2RH2 plus H2 squared is equal to S2 squared. Again, let's go back and see why we made these assumptions. That's because the information we have is the distance taken by the ship before disappearing, which is the summation of S1 and S2. Okay, let's work more on these equations and try to simplify them more. We take a square root of both equations from both sides. Then the next step is to factor 2RH1 in equation 1 and 2RH2 in equation 2. Why do we do that? That's because of the values of these two ratios, H1 over 2R and H2 over 2R. We know that the heights of the ship and the observer are millions of times smaller than the Earth radius, which is R. Therefore, we can assume that these two ratios are equal to 0 because when they're added to 1, they almost add nothing. So the next step is that we equal H1 by 2R to 0 and H2 by 2R to 0. So we have simpler equations. Now equations 1 and 2 are simplified to square root of 2RH1 is equal to S1 and square root of 2RH2 is equal to S2. Now we add these two equations and we know S1 plus S2 is equal to S. So we arrange this equation to write the Earth radius in terms of S, H1 and H2, and we know that the total distance is equal to the velocity u multiplied by the time t. So this is the final equation that we are going to use to numerically find the Earth radius. Now let's put the numerical values in the equation. We know that the velocity of the ship is 26 kilometers per hour and it takes 1 hour for the ship to disappear. We know the height of the observer, which is 1.69 meters, and the height of the ship, which is 36 meters. Let's take a look at the units. We see that the height unit in the denominator is meters, and that for the numerator is in kilometers. You can see that the hours cancel out each other. Now we need the unit of height in the numerator and denominator be equal. So we choose to multiply the numerator by 1000 meters per kilometer, because we know that 1 kilometer is equal to 1000 meters. Now kilometers cancel out each other, so we have meters squared in the numerator and meter in the denominator. Therefore, the final unit of the radius turns out to be in meters, and this is the final numerical value of the Earth as calculated at the harbor. Okay, thank you for watching this video. Please like and subscribe to see more videos like this.